All right. Well, good morning, everyone, to another Wednesday morning Safety Academy. My name is Anthony Schwann. I'm from Oliver. With us today, we have Larry Hagan and Dennis Falloon. Before I hand over the reins to them, I'm going to show you, as I always do, a quick overview of the Safety Academy webpage. It's located here at tampabaytrafficsafety.com/local area traffic safety academy in LATSA. Here you find information about the current webinar, a registration link, upcoming webinars and registrations for them. And this is the place where you download the previous webinars and recordings of them, as well as the PDH request form. There's always a question about, hey, where do we get the webinar or the presentation when it's done? And where do we get our PDH form? It's right here from the website. The URL for this website should be located in your email confirmation from the registration. And with that, I'm going to put up the screen to know how many people are in the room with you today, and I'll hand over the reins to Dennis for his introduction. If everyone can please answer the poll question. How many people are in the room with you today? It's just good for us to know.
Well, this is Dennis Falloon. Let me just start by saying that welcome, good morning, and this is the 8th webinar for this year of 2014, and there are 4 more left of this year, ending in December. I am a consultant with District 7, and today we're going to hear about empirical Bayes analysis for safety, and that will be presented by Larry Hagan, PE, and also a District 7 safety consultant. I was going to go ahead now and kind of run through my slideshow to give you a brief introduction, and wanted to mention to you that this academy is providing regarding safety-related issues to enhance your local safety programs in your roadways.
Dennis, you need to accept the request to show your screen.
Oh, I'm sorry. Where's that? Oh.
Do you see it?
I said show my screen. Did I take it?
Okay, now we're good.
Okay, sorry about that, folks. Anyway, these webinars provide information regarding safety-related issues to enhance your local roadways and your safety programs. This is the second series that began in March of 2014, and they usually run between 10 and 12 o'clock, 2-hour window. They'll end in December, on the 10th of December, and they're usually around the minimum of 1 hour, but no more than 2 hours, and that will always depend on the complexity of the webinar. As you know, you can register for these webinars through this link here on SurveyMonkey, and you can also go to the website that Anthony just showed you. You can also log in and register for those items. And also at the very bottom there, you'll notice the same website that Anthony showed you. You can go in there and you can look at, you can print the slides, or you can listen to the recordings. Now, like I mentioned, today we're going to hear about the empirical Bayes analysis for safety. And as you can see on the calendar, we only have 4 more remaining in this year. So just letting you know. And as Anthony mentioned, the form for PDH is out on the website. And Larry Hagan handles that, and he's the coordinator for those hours. And as you can see, you can download the form, and you would email it to Larry, and all that information is available for you to do this. And then you go to that website we talked about already. I talked to Stephen Benson in the safety office for District 7, and the AICP CM credits are in the process of being approved, so as soon as that is done, we'll notify you about it, let you know. currently we are working on the third series of topics that would begin in January 2015. And there will be 12 topics, one per month, and more information will be coming out on that. And if you have any information or questions or need assistance or have any need for anything regarding the Safety Academy, please contact me. You can call me or you can send me an email. And with that, I'd like to turn it over to Larry Hagan.
Let's launch a quick poll here while we transition presenters. We'd like to know how familiar you are with today's topic. And as always, with these webinars, if you have any questions, please type them into the chat, and we'll do our best to answer the questions during the presentation along the way, or hold it to the end depending on the question and how things are going along. But please utilize the chat. We'd like to have an active audience. All right, let's close that poll and see how. Looks like we have very few experts on the topic. About half the audience can't even spell empirical Bayes, and the other half has heard the name before. So you've got your work cut out for you, Larry.
Okay, very good.
You should have a request to share your screen.
All right, are you seeing my screen?
Yep, we're good.
Okay, very good. Well, good morning, everyone, and welcome to this webinar on the empirical Bayes analysis for safety. I really appreciate everyone attending here today. When you did have the choice of the FDOT specifications update webinar, I'm sure that just was very exciting to many people, but I'm glad you chose the empirical Bayes analysis for safety, and hope that you do get something out of this. I want to begin my presentation with my disclaimer. I always start with the disclaimer. We can talk about this for an hour. At the end of this, you're still not going to be an expert at empirical Bayes, but hopefully you will learn a little something. But what you hear today, hopefully will get you interested in empirical Bayes, and you can see how you can use it. And I will, at the end, give you some references if you want some additional information on using empirical Bayes in the studies you do related to traffic safety. I figured that there would be a lot of people that don't know a whole lot about empirical Bayes. I work with a lot of practitioners, and they hear this, and especially with the release of the Highway Safety Manual, they hear about empirical Bayes analysis, and I've heard many practitioners, many very knowledgeable, experienced practitioners who have decades of experience in safety work, asking the question, what is this good for? Why should I use it? What's it all about? And so the way that I approach this webinar is basically empirical Bayes for dummies, and I'm not calling anyone out there a dummy. Please don't be offended. I'm just saying I want to approach it at that level. There really is no dummies book like this, and I hope the folks that do the dummies books don't sue me for a copyright infringement. But that's basically the approach I took to the webinar, and so I'm taking the approach empirical Bayes for dummies in that it's a real introductory level intro into empirical Bayes analysis. And one of the things I hope to accomplish is to demystify the empirical Bayes. The way that it's used in the Highway Safety Manual and in other safety studies, I just want to clear up some of the confusion, what's it all about, and again, get the basic information out there, demystify some of this stuff, because again, talking to so many practitioners and people that are out there doing traffic engineering and safety work, they really don't have a deep understanding of empirical Bayes. Why should I use it? Is a question a lot of people have asked me. So hope to address some of that today. My real goal for this webinar is to bridge the gap that exists between the theory and the practice. if you're on the theoretical side or in a research area, if you go to TRB meetings and so forth, there's a lot of talk about empirical Bayes. But again, dealing with practitioners, the people out in the streets, the people that work for local agencies, the people that work for DOTs, they've heard of this empirical Bayes, but what does it really mean? And so I hope that this webinar kind of bridges the gap between that theory that the researchers all talk about in TRB and the practice, the people that do the work out in the field for local agencies or for DOT. So I hope that this goal can bridge the gap between some of the theory and some of the practice. And another thing that I took on in doing this webinar was something my father taught me many years ago. He told me if you really, really want to learn something, what you need to do is teach it. Because likewise, I'm a practitioner. I also spent some time on the research side of things. But I'm a practitioner primarily, and I still had those same questions too. What is this empirical Bayes all about? What can it do for me? Why should I use it? Why should I be interested in it? And so I found myself asking myself those questions, and I didn't have the answers. So again, learned from my father, if you really want to learn something, teach it. So I signed up to teach this webinar so that I'd have to research it and study it so that I would learn something about it. And what I hope to pass on to you today is some of the things that I've learned about the empirical Bayes analysis and how it applies to safety. And hopefully you'll find some information that'll be useful to you as well as we go through this. So in order to really start at the top level, high level, looking at empirical Bayes, we need to answer the big question, the basic questions, the who, the what, the when, the where, the why, and the how of empirical Bayes. So hopefully we can address those things as we go through this, and I hope that I answer these questions as we go through the webinar. So the way I'm approaching it, who developed it, what does it do, when should I use it, where should it not be used, why should I use it, and how do I use it? And again, by the time we get to the end of this brief webinar, hopefully we've answered these big questions, these high-level questions, at a level where you have some understanding of it. And so let's begin with who developed it. Now, I've heard a lot of people. I've been through highway safety manual training, and I've been through other training courses and other things like that where people have talked about the empirical Bayes method. And so I'm going to just ask people, is it fact or fiction? What I've often heard and taught is that Dr. Ezra Howard developed the empirical Bayes method. And so I started looking into this. Well, is that fact or fiction? And well, it turns out that that is fiction. I think if Dr. Ezra Howard, who is a brilliant researcher, and I'm definitely not taking anything away from him, I think if he had developed it, it would be called the empirical Howard method. But Dr. Howard did write a very important paper on the use of the empirical Bayes method in safety analysis specifically, and his paper is a tutorial on using empirical Bayes analysis. And at the end of the webinar, I'll give you a link where you can download his paper. I recommend it to anybody that really wants to get serious about empirical Bayes analysis. But he didn't create empirical Bayes. He was just one of the first. He wasn't, I don't think, the first, but one of the first to take the empirical Bayes analysis and apply it to traffic safety analysis. So then the question still remains, who developed the empirical Bayes method? And I found this really fascinating as I started digging into this. I mean, the history here just really, I thought, was fascinating. It was actually developed by the Reverend Thomas Bayes in the 1700s. And Thomas Bayes was born in London. He enrolled at the University of Edinburgh, and he studied logic and theology. Again, he was a reverend, and he's studying logic and theology. He was a nonconformist, which means he was one of those that did not belong to the official Church of England, and so he wasn't conforming because he lived in England. And it's really fascinating as you start looking at Reverend Bayes and the nonconformists, they were really a lot of what formed the foundation of the USA, of America, was these nonconformists that didn't want to be a part of the Church of England. Anyhow, in Thomas Bayes' lifetime, he is known to have published 2 works, one of them theological and one of them mathematical. His theological work, Divine Benevolence, or an attempt to prove that the principal end of the divine providence and government is the happiness of his creatures. And then he published a work in mathematics called An Introduction to the Doctrine of Fluxions and a Defense of the Mathematicians Against the Objections of the Author of the Analyst. That's a real long title, isn't it? Basically what it was, that second work, there was a man by the name of George Berkeley who wrote The Analyst. It was a paper where he criticized Isaac Newton's calculus. And so Thomas Bayes wrote this paper, published this paper, defending Newton's calculus against George Berkeley's objections. And so, anyhow, Bayes achieved some notoriety and fame and was elected as a Fellow of the Royal Society of London, basically on the strength of that second paper on the doctrine of fluxions. And he's not known to have published any other mathematical works during his lifetime. So where did the empirical Bayes come from, you may ask? Okay, so he didn't publish any other mathematical works. So where did this come from? Well, late in his life, Reverend Bayes took a deep interest in probability theory, and he started to study it. But when he passed away, his friend Richard Price took his manuscripts of this essay, an essay toward solving a problem in the doctrine of chances, and he presented that to the Royal Society, and that is where Bayes' theorem and the empirical Bayes and full Bayesian analysis and all of those things come from, is from this essay that was published, just after his death. It was published, Philosophical Transactions of the Royal Society of London, and again, that's the basis of Bayesian analysis. It's really interesting. Like I said, I just found the history as I started digging into it. It's fascinating. This is from the introduction by his friend Richard Price that took his manuscripts. And let me just go through this quickly. The purpose, is to show what reason we have for believing that there are in the constitution of things fixed laws according to which things happen, and that therefore the frame of the world must be the effect of the wisdom and power of an intelligent cause, and thus to confirm the argument taken from final causes for the existence of the deity. It will be easy to see that the converse problem solved in this essay is more directly applicable to this purpose, for it shows us with distinctness and precision in every case of any particular order or recurrency of events what reason there is to think that such recurrency or order is derived from stable causes or regulations in nature and not from any irregularities of chance. So that was the introduction to that article, the essay toward solving problem in the doctrine of chance, again, that is the basis for all Bayesian analysis. And basically, what the introduction says, what Reverend Thomas Bayes set out to do through Bayesian analysis, through this probability theory that he was developing here, that has now become one of the mainstays of statistics and probability, is he was trying to prove the existence of God and using statistics to prove the existence of God, and that's where we get Bayesian theory, the foundation of Bayesian theory. So again, just found it fascinating. Thomas Bayes is buried in what's called Bunhill Fields, where other nonconformists of the time are buried, including John Bunyan, author of Pilgrim's Progress, Daniel Defoe, the author of Robinson Crusoe, and Isaac Watts, and other notables. So, he's very well known and well respected in his time. And again, his theory, developed by this pastor that really had, not a whole lot of formal training in statistics, has stood the test of time. And you can see, if you can read, it says, in recognition of Thomas Bayes' important work in probability, this vault was restored in 1969 with contributions received from statisticians throughout the world. So the work that Thomas Bayes did in the 1700s has stood the test of time and resulted in what we're now looking at today, the empirical Bayes method. So that's the who. Now the next question is the why. Why should we use the empirical Bayes method? Well, if you've been in the research realm like I have, and you don't use empirical Bayes, your analysis is considered naive. If you do a before and after analysis and you don't use empirical Bayes, many in the research realm say you've done a naive empirical Bayes, or you've done a naive before and after analysis. And that always kind of got under my skin, just because I've been doing this kind of work for 25 years, and to have some grad student at TRB say my analysis is naive kind of got under my skin. But I think we ought to come up with something a little bit better than naive for it. But anyhow, you're considered naive if you don't use EB method where you should. The EB method is presumed to improve the precision of the estimates that you make, and presumed to correct for a regression to the mean bias. And so if you use the empirical Bayes methodology, it should improve the precision of your estimates, and it should correct for regression to the mean. And I'm going to talk about those things as we go through the presentation. So you hear all these things about the empirical Bayes, and again, it just is supposed to make your estimates much better and correct for all the regression to the mean bias. And so again, as someone that's a practitioner hearing this kind of stuff, you say, gosh, what is the empirical Bayes method? And kind of seems like magic pixie dust. You just sprinkle on a little EB and woo, now you got a wonderful analysis that is no longer naive. And so again, this led to, again, my interest in really digging into this, so I had a better understanding, and I hope that I can show you today it's really not magic pixie dust, but sometimes that's what it sounds like, or that's what it seems. Well, why should we use the EB method? Again, I mentioned Ezra Hauer's paper, and his paper gives some good reasons why we should be thinking about it for our safety analysis. And this is a quote from the paper. The empirical Bayes method for the estimation of safety increases the precision of estimation and corrects for the regression to mean bias. It's based on the recognition that the accident counts are not the only clue to the safety of an entity. Another clue is in what's known about the safety of similar entities. Now with that, I do need to put out a quick note here to my friend Rudy, who I'm sure is listening. Dr. Hauer uses accident here rather than crash. I know we call them crashes now, we don't call them accidents. But where you see accident, that's just because I'm quoting Dr. Hauer's work verbatim. He said accident all through his paper. So anyhow, so I know better. I know that we should call them crashes, not accidents. All right, so why should we use the EB method? Crashes are typically rare and random events. They're discrete, meaning that you'll have 4 crashes or 5 crashes. You're not anytime going to have 4.3 crashes or 4.7 crashes. And so crashes are rare, random, and discrete events. They're typically infrequent. We typically, when you look at an intersection or roadway segments, they don't happen too often. Otherwise, you get out and do something about it. And so that's really one of the reasons why we would use the EB method. It helps us where we have a small data size, where you don't have many crashes, don't have a lot of data to make decisions on. And so let me give you an example of that. Let's say we have a road segment where the expected crash frequency is 100 crashes per year, and you have 3 years of data. Okay, so you've got 3 years of data, and you're averaging 100 crashes per year. The average crash frequency can be estimated, and the standard deviation that we should expect can be computed as follows. We've got average of 100 per year. You have 3 years of data. So our standard deviation, plus or minus 5.8. So plus or minus 6 crashes a year is our standard deviation. And so what that means is you're going to see around 100 crashes a year, plus or minus, if you say 2 standard deviations, so plus or minus 12, basically. And so that would be the kind of crash experience you would expect, if you will, on that roadway. And so, again, the thing here is with 100 crashes per year, the standard deviation is 5.8% of the mean. You've got 100 crashes, 5.8 crashes, 5.8% of the mean. So that's fairly good precision. You've got a sizable number there and fairly good precision. But now let's consider a different road segment where crashes are not as frequent by far. So 1 crash every 10 years. So here crashes are very rare and infrequent. And again, you have 3 years of data. The expected frequency is 1 every 10 years. Average yearly crash frequency, again, standard deviation would be 0.1, a tenth of a crash per year, if you will. 3 years of data. And then you have that standard deviation is plus or minus 0.18 crashes per year. So the standard deviation in this case is 180% of the mean. So the standard deviation is much greater than the mean. So that indicates that it's very unstable and it's going to be tough to make a lot of useful predictions with that kind of data. So again, you have very poor precision, and again, what do you do with that information? Now, what is regression to the mean? That's talked about a lot. And again, from Ezra Hauer's paper, the other shortcoming of safety estimates that are based only on accident counts is that they are subject to a common bias. For practical reasons, one is often interested in the safety of entities that either require attention because they seem to have too many accidents or merit attention because they have fewer accidents than expected. Now, I don't know about all the people on the call, but I've never been with an agency that had the time to study locations that had fewer accidents than expected. We were spending all our time studying locations that had too many crashes. And that's typically how most agencies are. You study the things that have too many crashes. But in both cases, if you were to estimate the safety using the accident counts only, the estimate is biased because you're looking at just the ones that need attention. And so the existence of this regression to the mean has been long recognized, and it's been known to produce inflated estimates of countermeasure effectiveness. And in his paper, Dr. Hauer refers to one study that was published. It was done in Detroit. 3 intersections were treated, and they had a low-cost treatment done at these 3 intersections in Detroit. And at the 3 intersections, one of them experienced crash reduction of 44%, one of them experienced 48% crash reduction, and the other 57%. So, I mean, it sounds great. Wow, we've got tremendous crash reductions at these intersections, and that's a good positive thing. However, these locations were chosen because they had high crash rates. And so the thought is, well, maybe the crashes would have come down even if we didn't do anything. I mean, maybe they were just experiencing a real high year, just the way things fall out, randomly. And it turned out that Dr. Hauer looked at these intersection studies and said the crash rate or the crash frequency or the crash severity at those locations that were chosen were higher than 95% of the intersections. Basically, I suppose they were on the 5% report, if you will. And so these were the top 5% where lots of crashes are occurring. And so again, if you are just studying the ones that are really, really high, and you make a treatment on those, well, have you really measured the effectiveness of the treatment? And so that was Dr. Hauer's criticism here, was there was no correction for return or regression to the mean bias in the study at all. And we'll come back and look at that a little bit more. I showed this before. Why should we use the empirical Bayes method? It increases the precision and corrects for regression to the mean. It's based on this recognition that the crash counts are not the only clue to the safety. Another clue is what's known about the safety of similar entities. And I want to just highlight this because this truly is, if you will, the philosophical underpinning of empirical Bayes and its applicability to safety analysis, that another clue is what's known about the safety of similar entities. Dr. Howard goes on that a sensible estimate must be a mixture of the two clues. So the crash experience plus the experience at similar entities. And to estimate the safety of a specific segment of a rural two-lane road, one should use not only the crash counts for that segment, but also the knowledge of the crash frequency of other such roads in the same jurisdiction, is what he's saying there. And so this is how we get a sensible estimate of safety. So what does all this really mean? And again, how do we use this? What does this mean to us? And I remember, back when I took, basic statistics, one of the things that my statistics professor gave is kind of a rule of thumb. There's a sample size of at least 30 is needed to be statistically significant. I mean, that was just kind of a rule of thumb that I remember my basic statistics professor telling me. And Anthony, why don't you put the poll question out there?
Yep, it's on screen right now.
All right.
Just trying to make sure everybody's awake here. An interactive webinar.
Yep. So how many people also heard the same kind of thing in your basic statistics or some of the early statistics work that you might have done? So
got about 70% of the people have voted. Give them another couple seconds here. All right, let's see how we did. Let's show the responses here. It's like 60% of the audience had never heard that, and 40% did. That's with 80% of the audience responding.
Okay, so I was a little surprised, not a majority of them, but okay, but 40% of the 80% that did respond had heard that before. So that's somewhat encouraging. I'm not out here by myself and hearing that. So anyhow, it's not a hard and fast rule. It's a rule of thumb, is what my professor had told me, that at least 30 is what you should be shooting for. Of course, the more the better. Well, what do we have when we are doing traffic safety analysis? What do we typically have when we're looking at safety? You may have 3 to 5 years of crash data. And we may have 3 to 5 years of the traffic data, ADT data, to go with that crash data. And hopefully we've got 3 to 5 years of geometric data to go with that data. And so we've got the whole package of data, if you will, the crash data, ADT data, and we know what the roadway conditions were, the geometry and traffic control and all that kind of stuff. But what that really gives us is like 3 to maybe 5 data points. And so the question is, with just 3 to 5 data points, can we draw statistically valid conclusions? And again, that's where, often when you present at TRB or something, your analysis would be labeled naive because you only got 3 to 5 data points. How can you draw anything useful statistically if you only have 3 to 5 data points? So can we draw statistically valid conclusions? Yes, you may show an increase or a decrease or whatever, but is that a statistically valid increase? Is it a statistically significant increase? And so, again, that's the kind of thing, including some empirical Bayes analysis, may help us to overcome. And so how do we overcome that data limitation that we have, that severe data limitation, only 3 to 5 data points? Well, of course, we can apply magic pixie dust. Just whip out your bag of pixie dust and sprinkle that on. But in case you're out of magic pixie dust, don't have any more, more in your bag. Well, how do we overcome a lack of data? Add more data. So if you don't have enough data to really be statistically significant, just add more data. Well, where do we get more data? Well, you could wait 30 years and collect 30 years of data, but hopefully over the course of 30 years you're going to make roadway improvements, you're going to add turn lanes, you're going to widen the road, you're going to find things that are going on. And so your data will be somewhat corrupted because you've changed the geometry over the course of that 30 years. So that's really not the most reasonable thing. And so the other approach is to gather data from similar sites. And so again, that's what Empirical Bayes is really all about. Empirical Bayes assumes that the crash experience for 30 years at your one site is approximately the same as the crash experience for 1 year at 30 similar sites. And that these sites are really similar, and so the crash experience, if we average it over those 30 sites, would be roughly the same as your one site if we had 30 years of data. And so, I mean, that's, again, the foundation for application of the EB method. And thinking even beyond 30 years to hundreds of years or 100 years, you know, the crash experience of 100 years at your site is roughly the same as the crash experience at 100 sites. And so again, that's the foundation for application of Empirical Bayes, is that we can take data from other similar sites and believe that it applies and is helpful to us in analyzing our site. And so again, one of the assumptions in the Empirical Bayes method is that the crash experience really not random, but that it's predictable and deterministic. I mean, in the long haul. I mean, yes, it's random in the short haul, but in the long haul, when we look at big averages of lots and lots of sites or lots and lots of years, and especially lots and lots of years at lots and lots of sites, we average that stuff together, and crash experience then is something that's predictable, and it is deterministic. We can come up with an estimate for how safe that particular roadway or that intersection will be. And so again, looking short-term versus long-term on the figure here, let me grab my spotlight thing here. So looking here, the green line, hopefully you see right here the green line, that is a 5-year average crash frequency. You can see this 5 years is a lot different than this 5 years. But if you average many, many years, and especially incorporate data from other sites, or maybe you have 30, 50, or 100 years of crash data, then here's your average or expected average crash frequency. And so again, you can see short-term little blips, and it hops around because they are random and discrete events, crashes are, and so it will flip around a little bit as it goes through time. But over long periods of time, and especially when you combine several sites, you get that blue line there, the expected average crash frequency. And so what you really want to be looking at is my site consistently way above this expected average crash frequency? Is it consistently below it, which would be a great thing? Or is it like this, fluctuating above and below it? So this is probably a site that's relatively average. It's fluctuating above and below this expected average crash frequency. So this is probably, again, a fairly average site in terms of its crash performance.
Larry, there's a question in the chat about the size of the population. They've heard that it depends on the size of the population being sampled. Can you speak to that?
Well, I mean, absolutely right. Yeah, it would depend on the size of the population. I mean, I'll try to get to that. If not, let's make sure I get to that when I get to the end, because I think some of these slides may address some of that. But certainly we will talk to that some more.
Okay.
All right. Now, regression to the mean, again, you hear that a lot, especially since the Highway Safety Manual came out. That is one of the things that you hear talked about a lot, and one of the things Empirical Bayes is believed to correct for. And again, if you just have your crash data here, what typically happens, here we go this year, we've got a few crashes go down, then all of a sudden, oh my goodness, crashes have gone way up. We've gone from way down here. Let me get my highlighter thing going again. So you've gone from way down here to you go up to this many crashes and then up to this many crashes, and you say, wow, we've had a huge increase in crashes. And so we put in some kind of treatment. So here we put in a treatment and crashes start going down. And it's real easy to say, wow, we were up here and now we've reduced crashes down to here. We've had this big, huge effectiveness. And that's the kind of thing in that Detroit study they were talking about. Huge safety benefits from those intersections, from the low-cost treatments that were applied. But if we really look at, was that just a short-term trend at those intersections? If the blue line here is the real average crash frequency, then the real effectiveness of the treatment is this part down here. This is the actual reduction that's due to the treatment. And this stuff up here is the regression to the mean correction. I mean, that probably had we done nothing, our crash experience would have come back to our average anyhow. And so that's what the regression to the mean, it's regressing back to what our mean crash frequency would be. So anyhow, that's what regression to the mean is all about. It's, how much of the reduction can we really attribute to the treatment versus how much it would have likely happened had we done nothing. Oops.
With sample sizes, Larry, do you have any thoughts on studying locations looking at just fatal crashes?
Again, if you're studying locations just with fatal crashes, again, your sample size is going to be small. And so you probably will need to have many years of data, or again, the empirical Bayes type thing where you pull in the data from other similar locations, similar intersections would be very helpful. And so again, when you're looking at fatal crashes, and that's a really important point, I'm glad you brought that up. One of the things, you have to be careful using number of fatalities versus fatal crashes. I remember years ago I was looking at the data in this one county up in North Florida, and they had typically 1 or 2 fatalities every year, and so one year it'd be 1, next year it'd be 2, next year there'd be 0, then one year there may be 3, and so, I mean, they were averaging, 1.5 or so. Then all of a sudden one year there was 10 fatalities, and so I went to the district safety engineer. I said, man, what's happened there? They went up to 10 fatalities. And, well, a cement truck hit a school bus and killed 8 people in that one crash. So that's one of the reasons you want to look at, especially when your sample size is small like that, look at fatal crashes rather than fatalities, because, again, that one crash killed 8 people. And so it seemed to throw the statistics way out of whack and say, wow, we've got, lots more fatalities than we had. But in terms of fatal crashes, it was right about average. And so was it a high fatal crash location? No. Was it a high fatality location? Yes, because it had one crash that killed a lot of people. But to the question of sample size, again, that's one of the things empirical Bayes will help do, is you're increasing your sample size by including data from other locations that you believe to be similar or somewhat representative of your location. And so again, that's a good part of what the EB is all about. All right, so how do we use empirical Bayes? The task before us is to make use of these 2 clues for the safety of the entity: the crash record of the entity and the crash frequency expected at similar entities. Let me see if I can get rid of this thing. Okay. So let's look at this here. The task, again, is making joint use of the 2 clues. The expected crash frequency at similar entities is determined by a safety performance function. So how do we get, what the crash frequency of similar entities would be? It comes from our safety performance functions, or SPFs. And we find those in the Highway Safety Manual. And let's see. The EB procedure, this is what it's all about. The unexpected here is the number of expected crashes is equal to a weighting factor, the little W there, the W, times the number of predicted crashes plus 1 minus our weighting factor times the number of observed crashes. Okay, and so yeah, these are the definition of the things in the formula. The expected average crashes is what we're looking for. Basically that blue line that I showed you on the charts. And we get it from the predicted crash frequency that comes from our SPF multiplied by a weighting factor, and then 1 minus that weighting factor times the observed crashes. The weighting factor is going to be something between 0 and 1. And so the higher the weighting factor, the more emphasis you're putting on the SPF. If you have a very low weighting factor, you've got more emphasis on your observed data. And so again, we'll look at that as we go through it mathematically. Basically, what it leads to is if you have more years of observed data, or if you have lots and lots of crashes, a big sample size, the predicted stuff, the stuff you get from the SPF, will not be weighted heavily. If you have good and lots of observed data, it's going to lean towards the observed data. If you don't have much observed data, the EB process is going to lean towards the predicted data because, again, the assumption is those other sites are similar to your site, and we have many other sites there that are studied, and so we've got a lot more data there, and so we're going to lean heavily on that. But if your site has a lot of data, then it's more statistically valid, if you will, to lean on your data. And so the observed data will be weighted much more heavily if you've got lots of observed data, lots of crashes, or lots of years of data. And so I think that's an important answer to that question of sample size and how it's accounted for in the EB process. Okay, that weighting adjustment factor, that W, is shown here. This is the formula, and it's shown there before you, and the denominator of it, 1 plus K, which is this over-dispersion parameter that's a parameter of the SPF. So it's something that's related to the SPF. So 1 plus this K times, and the sum of the predicted crashes for all the years of study. So again, if you have lots of years, that number is going to get big. If you have lots of crashes, or if it typically predict lots of crashes, again, the denominator is going to get big, so W is going to get small, and so the weight on the SPF part of it will be fairly small, and the weight on your real data will be much greater. So if you have lots of data and lots of good data, your data is going to weigh very heavily. If you don't have much data, if you don't have a big sample size, then the SPF data is going to weight a lot heavier. So let's run through an example. Try to stay with me through this. We'll go through this kind of quickly. 2-lane rural road segment. Let's say we've got 1.7 miles in our segment, and the AADT, let's say it's, just to make it simple, it's stayed constant at 6,500 for the last 3 years. Our observed data, we had 6 crashes one year, 9 crashes the next year, and then 4 the following year. So we got 3 years of data. I'm going to assume base conditions for the SPF, and I'll come back and explain that in a little bit. We'll cover that a little bit later, but we're going to just make it simple. We'll assume base conditions for the SPF. And so the question is, what is the expected crashes? Again, what's that blue line that we showed, the average number of crashes we should be expecting. And so how we get to the empirical based procedure, Again, this is what we're going to be looking for. You know, what's our expected crash number that we can expect, or that blue line that I showed in that graph. And we've got to also apply our weighting adjustment factor into the equation. So let's find this predicted, find the predicted, and this is from the safety performance function, and this comes straight out of the highway safety manual. And you know, this is for a 2-lane rural highway. This is the safety performance function. You know, to get the expected average crashes on a 2-lane rural roadway, you put in the AADT, put in the length, and you know, away you go. This has always been, you know, since the Highway Safety Manual came out, this has been one of my pet peeves, is the this last term at the end of that equation, e to the negative 0.312 power. It makes it look like this is something other than a straight line, because one of the things they tell you is that, well, we know that crash experience isn't linear, and so, you know, they kind of made it look like it's not a straight line. But in reality, this is a straight line. You know, if you double your traffic, if you double the AADT per this formula, you're going to get twice as many crashes. If you triple your AADT, you're going to have 3 times as many crashes. And so, again, it's just been one of my pet peeves, is they've been kind of, I think, intellectually dishonest the way they presented it in the manual, because really that's what it is 0.732. It's a constant, and they ought to really show it as a constant, I think. But anyhow, what we see here, here's our formula. This is how we get our predicted number of crashes. And so we plug in our ADT. We said 6,500, 1.7 miles, and we multiply all this stuff across, and we get an expected number of crashes. 2.95 crashes per year. That's our expected crash frequency. Now, we're going to skip the next step because I said we had base conditions. Now, the base conditions, they're covered in the Highway Safety Manual. They tell you what the base conditions are, and you know, basically it's stuff like you have 12-foot lanes, you have 6-foot shoulders that are paved, level terrain, and all those kind of things. And so those are base conditions. And so basically what that means is all these CMFs you see up here, crash modification factors, all those are going to be 1 because I assumed base conditions. But if you had something different, if you had narrow lanes, there would be a crash modification factor. You apply to that number that we just computed. Or if you had less shoulder width, there'd be a crash modification factor. And for all those different things, you apply a crash modification factor. And then the last thing, the C sub X. There's a local or regional adjustment factor. Florida DOT, the central office, has done some work with one of the universities to come up with some those correction factors for Florida, and so you know, that's where you would get that information and apply that to this if you were doing that. I'm going to assume that all those things are 1, and so what we computed are from the SPF is our predicted crash number. So 2.95 is our number. Now look at the over dispersion. This, you know, the over dispersion parameter K, this formula comes straight out of the Highway Safety Manual. And so it's, if you're interested, it's page 10-16 of the Highway Safety Manual gives you this that is applicable for 2-lane rural roadway segments. And so it's basically, you know, 0.236 divided by the length. And so for us, our length of 1.7 miles gives us a K of 0.139. So now we take that, plug it into our weighting factor formula. And our weighting factor formula, we plug in the 0.139 that we just computed for K. Our predicted value, we had 3 study years with 2.95, and so we plug and chug on that. And this is our weighting factor. So 0.449 is our weighting factor. And now we go and compute our expected crashes. Again, here's the formula for that. We plug in our 0.449, which again, this is the weight for how much weight we're putting on the predicted stuff from the SPF. So the 0.449 is multiplied by our 2.95, the predicted crashes, and then 1 minus 0.449, or basically 53.1% weight is put on our observed crash frequency, which is the average of the 3 years, 6 plus 9 plus 4 divided by 3. And so, again, more weight in our case is put on our observed crash frequency because we had 3 years of data. And so we work all that out. And so our expected, where that blue line would lie for us, is about 4.81 crashes per year. So just a little under 5 crashes per year is what we would expect on this roadway. So again, it's real simple, fairly straightforward. It's just a matter of looking up these things out of the Highway Safety Manual, and it's fairly simple, plug and chug to work your way through it. So that's our expected crash frequency. And so you can see we're, based on those 3 years, we have 2 years that are above it, 1 year that's below it, so we're somewhere close to it. We're hanging close to it. But it's something we'd want to...
In one of the formulas, you had a 10 to the minus 6.
Yes.
Where did that come from?
That's just hard-coded in there. It's basically what you're doing is you're taking the AADT and you're multiplying that by 365 days per year, and the million, the 10 to the minus 6 is basically, we talk about crashes per million vehicle miles. And so you got daily traffic, it's our average annual daily traffic, and so that's the 365 multiplier is converting days to years, and it's really just working out the units. And that, again, we typically talk about crash rates in terms of crashes per million vehicle miles, and so that's where the 10 to the minus 6 came in. It's just hard-coded. It's a constant in there in the equation. So excellent question. Yeah, that's, again, if you look in your Highway Safety Manual, it gives a little bit of discussion. It really doesn't give much discussion and development of the formulas, but essentially that's it. If you've been around doing safety analysis for many years, you recognize the 365 as converting daily traffic to annual traffic, and the 10 to the minus 6 is you're dividing it because your crash rate is typically, or your crash frequency is typically expressed in terms of crashes per million vehicle miles. So I hope that does answer the question there. Good question, though. Okay, now one of the questions I had at the beginning, where should EB not be used? And so, it discussed it so far, and it sounds like this is something that could be helpful in many analyses, but the Highway Safety Manual gives some information here where it's not applicable. And the first part of this, the EB method is only applicable when both predicted and observed crash frequencies are available for the specific roadway network conditions for which the estimate is being made. And then it goes on to say, where only a predicted or only observed crash data are available, the EB method is not applicable. So if you don't have both a prediction and observed crash data, you got to have both. If you don't have both, it's not applicable. And so basically what it's saying in a nutshell is if you don't have an SPF, if you don't have a safety performance function, you cannot use empirical Bayes. So you have to have an SPF to develop the estimate so that you can use the empirical Bayes method. So looking at the Highway Safety Manual, the SPFs that are available, rural 2-lane roads, there's an SPF, the one we looked at for segments on a rural 2-lane roads. There's SPFs available for intersections. For rural multi-lane highways, again, segments and intersections, there's SPFs in there. Urban and suburban arterials, there's SPFs for segments and intersections in there. There's some recent stuff on freeways. There's nothing in the Highway Safety Manual, but there's some stuff that recently was done through TRB that has come up with SPFs for freeways. So these are the ones that are available right now as we speak. is the ones shown on the screen, but there's some important things to understand about this. If you open up a highway safety manual and you go to the rural multi-lane highways, what rural multi-lane highways means is rural 4-lane highways. And so it clearly tells you that facilities with 6 or more lanes are not covered by Chapter 11. Now, some of the folks, federal highways, are saying, well, you can kind of sort of use it with some cautions. Well, according to the manual, the researchers that did the studies and put the stuff in the manual, the manual says facilities with 6 or more lanes are not covered by Chapter 11, which is the predictive model for multi-lane highways, which again is 4-lane highways. So again, if you got a 6 or 8-lane multi-lane rural highway, there is not an SPF, and so therefore you can't really use EB. Likewise, for urban and suburban arterials, these are the cross sections that are covered in the urban and suburban arterials sections. 2-lane undivided arterials, 3 lanes with the center 2-way left turn lane, 4-lane undivided, 4-lane divided, and 5-lane with center 2-way left turn lane. And again, 6 lanes, 8 lanes, 8-lane arterials, 6-lane arterials are not covered by the Highway Safety Manual. You have no SPF. You can therefore not use EB since you don't have an SPF. So, I mean, if you have some other way to get other data, or if there's some SPF that you've developed based on studying other 6 or 8-lane arterial roadways, you can use that. But you're not going to find it in the Highway Safety Manual, is what I'm saying here. All right, with that, we're getting towards the end. I hope that I have given you a little bit of a flavor for empirical bays and how it can be used for safety. Hope we know now the answer to the question, who developed it, was Reverend Thomas Bayes. What does it do? It helps correct for regression to the mean, and also it helps fill in data when we don't have enough. When should we use it? When we have crash data and safety performance function available. So when we have both those things, that's when we should use it. And when should we not use it? Well, if you don't have a safety performance function, you really can't use it. Why should I use it? It does give you better precision. And how do I use it? Use it very, very carefully, because, again, you can really get messed up if you don't use it properly, and you can come to some erroneous conclusions if you go in with erroneous data. So with that, I want to show you, and you'll have this in the PDF of this, but Dr. Hauer's paper is the thing at the top of the screen here. It's posted on the website at Iowa State University. And again, if you're really interested in finding out more about the use of empirical bays with regard to traffic safety, I really highly recommend his paper. It's a tutorial on its use in highway safety, and so it's really, really good. I recommend that strongly. And so, again, that's reference for that. And I got the information on Thomas Bayes from Wikipedia and additional information out of the Highway Safety Manual. So these are some of the references of what I used. But with that, I'm going to say that's all, folks. That's about the end of my presentation. A couple quick little closing things. If you do want your PDHs, yes, complete the form and send them to me. You can just email them to me or fax them to me, whatever is easiest. And I just want to say, if you've never done that, said, oh gosh, I don't want to take the time to complete the form, it's really, really simple. And especially once you do it the first time, just save it. Type in your name, your PE number, your email address, and then for each webinar, it's a pull-down menu. So you just go up here, click here, and it's a pull-down menu, pull down to the workshop name, and then go up to your file menu up here and hit File, Send, and email it to me. So, I mean, it shouldn't take you 20 seconds to do it. So if you're interested in the PDHs, it's a really, really simple thing. Just open up the form, and especially once you do it the first time where you have to type this stuff in, save that, pull it up the next time. all you got to do is click the pull-down menu and change it to the current topic. Go up to your file menu and send it, and you can email it directly to me, and that should keep it fairly simple. Oops, I didn't mean to do that. All right, with that.
Well, we've got a quick poll here to do, and then we'll see if there's any questions in the chat.
Yeah, so as the poll is up, if you do have some questions or comments, do enter them in the chat pod.
Yeah, let's see one question in the chat pod that has not been addressed. All right, we've got about 76% of folks that have voted. I'll show the responses for that. Close and share. That's pretty good, Larry.
Okay.
Close to 80% learned a lot. No one said they hadn't. No one said it was everything they had seen before, and no one slept through it. So, or maybe the poll question didn't wake them up, so they're still snoozing. Who knows?
All right. Well, I hope that everyone did learn something that's useful to you, and I'll do my best to answer any questions that anyone wants to bring up.
I've seen a question in the chat about the roadways with 6 or more lanes. Do you know anything about SPFs for them, if they're going to be developed?
They will be developed. Yeah, one of the things with the Highway Safety Manual, this was the very first edition of the Highway Safety Manual. And what that means is, this is the beginning point. And I was around for the beginning, if you will, for the Highway Capacity Manual. I mean, there was, 1965 Capacity Manual. I wasn't around for that, but I had just entered graduate school when the 85 Capacity Manual came out. And so I was there at the forefront of that and had the just great privilege to be working at the McTran Center at the University of Florida at that time. And so one of the things I saw was the 85 manual. Like I said, it was really the first modern capacity manual. And I saw firsthand how that really started a lot of people researching things that can be improved in highway capacity analysis. I mean, my master's paper, my master's work resulted in changes in the highway capacity manual, some improvements to capacity estimation and delay estimation. And I know that's going to be the same thing with the Highway Safety Manual, is that there's loads and loads of researchers out there researching this stuff, trying to fill in those gaps, trying to validate the data, trying to expand the data pool. Because really, you get deep into the data that's in the Highway Safety Manual, and some of this stuff isn't based on a whole lot of data yet. And so I really expect a lot of things are going to change, and one of the things that I know is going to change is those gaps are going to be filled, 6-lane, and 8-lane highways. And, one of the other big gaps there, if you will, is we've got, urban and suburban arterials, but there's no urban collectors, if you will, or urban residential streets or something like that. I mean, urban local roads. There's not a SPF, if you will, for those kind of streets. And so I really expect a lot of those holes, a lot of the things that aren't there, a lot of the things where people say, well, that really doesn't apply. Grad students all over the nation are going to be working on their master's and PhD papers, coming up with SPFs and the things to fill in those gaps that presently exist. So that's an excellent question. But yeah, I would certainly expect to see those things that we don't have right now come out, and in the next version of the Highway Safety Manual and in subsequent TRB papers and stuff like that. And it's just going to be one of those things, getting those research results out to the practitioners. That is, again, one of those bridges. Like I said early in the presentation, what I hope to do here is bridge that gap between the research that's out there, the theory, and practitioners, the people that are actually, using this stuff in the field. And it's just like the freeway stuff. The freeway stuff is fairly recent. I think it was right at the beginning of this year that it was put out there, published. But again, it's not in the Highway Safety Manual. But if you go to the Highway Safety Manual webpage, it points you to those updates, the freeway updates, and of course things like the crash modification factor clearinghouse that has the latest, greatest information on crash modification factors. Any other questions show up there, Anthony?
Yes, we have. On your end, you're able to pull them up as well. They're in the, the chat box. But,
Okay.
No, it says there are some drastic changes that are being made to the old critical values versus the new ones, the new safety ratios.
Mm-hmm.
Can you quickly compare the old methodology with the new methodology?
Oh gosh. Yeah, the old methodology. It's similar. Because a lot of the new methodology, if you will, has evolved up over the years from the old methodology. The application of the empirical Bayes, though, in particular, is something a little different. It's because typically what most people did was what they call naive analysis, where you've got 3, 4, 5 years of crash data before, and maybe 1, 2, 3 years of crash data after, and your before and after is based on your local crash data. I think the empirical Bayes analysis is fairly new, and again, I'm a little bit, honestly, I'm a little bit, I won't say skeptical, but cautious in using the empirical Bayes, again, because the data sets for some of the SPFs aren't that large either. And there is a lot of variability, and I think that's another thing that's going to really be tweaked out over the years by a lot of the graduate students. I was looking for, I had made a slide of this and I couldn't find it, but if anyone wants to just take a note and look at this stuff themselves, if you go to your Highway Safety Manual and you look on page 3-41, that's in volume 1 of the Highway Safety Manual. I've got it here in front of me, but it shows some of the raw data that was used to derive the safety performance functions, and you see a pretty good spread of data. It's a pretty good series of shotgun blasts all over the place. And so again, that's page 3-41, and it continues on 3-42 and 3-43 in the Highway Safety Manual. You can see that the figures show there is a little bit of spread in the data, but what comes out of the SPF is a straight line that goes through that data. And so there is some dispersion in the data. There's actually a pretty good bit of dispersion in the data. And so the question, becomes how similar are those similar sites? And so, again, the theory behind the EB analysis is that if we bring together enough sites and we average them all together, we can somewhat account for some of the differences that might be there. But still, I think you're going to see more crash modification factors added as more of these things that change from site to site are really better understood. So what I truly expect, and again, this is a great parallel to when I was back in grad school doing the highway capacity manual stuff, it's a great comparison to that, is what I predict 20 years from now. It's going to be just like what happened with highway capacity manual, in that the highway capacity manual, as all these researchers started adding stuff to it, tweaking it, and adding new factors and getting more data, the methodology has become much more complex. And it's gotten so complex, like for instance for signalized intersections, it's gotten so complex that you really have to do it by software. When the 85 manual came out, it was set up to be done essentially in spreadsheets, and so you could do it manually if you wanted to. No one in their right mind really did, because it would take you forever, or I mean, I've done it myself, and it would take 6 or 8 hours to analyze one intersection, whereas when you do it with the highway capacity software, it's just a matter of minutes. And so I really see the same thing happening in the future with the Highway Safety Manual, is that we're going to be adding more features to it. We're going to get to where we have more factors we can account for. We're going to get to where we know more. And the analysis will get more complex. We'll get better answers, but it's going to get more complex. And so 20 years from now, if you want to do a safety analysis, you're going to be running the highway safety software, the HSS, if you will, and run the HSS to get your safety results, your predicted safety values, and all the data out of your safety predictions, and the empirical Bayes analysis will be built into it, and all that kind of stuff. So that's really where I see it going, is eventually, if we want to do a safety analysis, we'll whip out our HSS on our iPad or laptop or tablet computer or whatever, or smartphone. We'll probably have HSS on smartphone app or whatever in 20 years. So. Any other questions in the chat pod? I kind of started waxing philosophically there, didn't I?
There was a comment there while you were, that's just kind of a comment that they were responding, specifically in court in front of an eminent domain judge. When you're justifying a take and avoiding damages, complex is not necessarily good when talking to the general public. So they're just kind of
I agree
philosophically alongside with you, saying that it's kind of too bad that things have gotten so complex.
Yeah, and I mean that is the challenge. Is we have the complex analysis, and we got to make it simple where people can understand it. And that's one of the things I tried to do with this webinar today, because, again, there's so much information, so much misinformation, if you will, out there about empirical Bayes, and it sounds like it's so complicated. And, well, I, again, was trying to demystify it, and I hope I succeeded in that for at least some of the folks in attendance here today. I hope you did learn something, and I hope I did demystify it some.
Well, based on the little exit poll, 98% of the people, or no, 90% of the people learned a lot today. So.
Well, that's great. That's great. I'm glad.
Which has been accomplished.
Larry, this is Dennis Balloon. I wanted to thank you for today's presentation. And so, Anthony, you can do what you need to do to close out this.
Yeah, well, thank you, everybody, for attending. I mean, if there's no other questions in the chat, I will end the recording. And, again, the PDHs and the PowerPoint, or the PDF of this PowerPoint, as well as the recording of the entire presentation, will be posted on that Tampa Bay Traffic Safety webpage. So if you're interested in that, please access it from those web pages.